Bismillahirrahmanirrahim. My name is Abira Rizwan. I am a student of MS Chemistry at University of Management and Technology. I am from first semester batch 5. The course code is Chemical Industry. I have made a presentation on topic of acoustic ultrasound and cavitation reactors under the supervision of Dr. Hamad Majid. So let's start our presentation of this review article. First of all, we will discuss the contents that will be discussed in this review article, which includes the abstract. After the abstract, we will discuss an introduction to sonochemistry and cavitation. Cavitation is the key phenomena occurring in cavitation and acoustic reactors. Therefore, it plays a very important role, and we will discuss it in detail. The introduction includes the introduction and study of ultrasound, applications of ultrasound, and then we will discuss ultrasonification and cavitation, which includes mechanisms of acoustic cavitation, types of cavitation, cavitation threshold, activation sites in sonochemical reactions, cavitation near solid boundaries. After discussing and having a brief introduction about cavitation, we will move forward to acoustic ultrasound and cavitation reactors, which is our main subject, and the next particle of this article, which includes the factors that should be considered by designing activation reactors. Next, we will discuss about optimization of operating parameters such as temperature, pressure, and various parameters that should be taken into care and taken into account while designing cavitation reactors. Next, we will discuss cavitation yield, which is very important and that should be kept in consideration while designing cavitation reactors. We will move to the next segment, which is types of cavitation reactors, which include hydrodynamic cavitation reactor, acoustic cavitation reactor, and optical cavitation reactor. Among them, acoustic cavitation reactor, we will discuss about the basic elements consisting of transducers and horns, the reactors, their designs and geometries, which have the number of designs including ultrasonic cavitation bath, cup horn system, ultrasonic probe system, flow system. Then we will discuss about qualitative considerations for reactor choice, scale-up, and optimization. Next, factors affecting performance of cavitation reactors. There are a number of factors that affect the performance and which are described in this content page. After that, we will move forward to intensification of cavitation process, which includes the recent advances and recent study which is actually done in the cavitation field, and which is mainly focused on the improvement and enhancement of cavitation process. After this, we will discuss applications of cavitation reactors, which are the wide and diverse range of applications in various domains, health and safety aspects of laboratory reactors, limitations of ultrasonic reactors. After that, we will conclude the article with concluding remarks, and at the last, there will be references. So first of all, let us discuss the abstract. This article provides a compact summary exploring the realm of acoustic and cavitation reactors, delving into foundational principles of sonochemistry and cavitation. It covers a detailed analysis of acoustic and cavitation reactors, investigating various types and designs and at improving cavitational activity. Additionally, the discussion includes the optimization of operating parameters for these reactors. Beyond theoretical considerations, the article explores the extensive applications of these reactors, showcasing their versatility in diverse fields. Furthermore, recent advances in acoustic and cavitation reactor technology are highlighted, offering insights into the cutting-edge developments shaping this dynamic and interdisciplinary field. So this was the abstract. Let us now move forward to the introduction of sonochemistry and cavitation. In cavitation and acoustic reactor, the major phenomena that is the heart of cavitation reactor is actually the cavitation. So first of all, discussing about the cavitation, the study of cavitation comes under the field of sonochemistry. So we can say that sonochemistry is the field of chemistry that deals with the study of effects of ultrasound that are the sound waves at the frequencies above the range of human hearing on chemical systems. So basically, in sonochemistry, we link the cavitation to the chemical systems. So there is a linkage and relation between cavitation and chemical systems. What is the ultrasound? The ultrasound is a main concept, and these are the waves which are particularly of the interest in cavitation process. So ultrasound is a sound having frequencies greater than 20 kilohertz. In healthy young adults, ultrasound is the upper audible limit of human hearing. Acoustic waves, physical principles apply to any frequency range, including ultrasound. Ultrasonic devices operate at frequencies ranging from 20 Hz to several gigahertz. So basically, ultrasonic waves, they are of the particular interest in acoustic cavitation, particularly in cavitation process. Besides the cavitation, there are the vast and diverse applications of ultrasound itself. As we know that ultrasounds are particularly useful in detecting objects, measuring distances. They are also ultrasonic in the form of ultrasonic imaging or sonography. They are also very useful in the field of medicine. Ultrasound is also useful in detecting flaws during non-destructive testing of products and structures. In the industry, ultrasound contributes towards cleaning, mixing, and accelerating chemical processes. So these are the general applications of ultrasound. Beside this general application, which we are familiar with, there are also some applications which are mainly associated to the activity of cavitation reactors. And these are basically the cavitation itself. So these are actually the high power application of ultrasound. So high power application involves the application in cavitation. Intensity of ultrasound can be very high, above 10 watts per square centimeter, leading to introduction or induction of cavitation in liquid medium. Such high intensities of ultrasound can induce chemical change or produce effects by direct mechanical action and can inactivate microorganisms. So in this way, ultrasonic waves, they have the particular application, a main application in cavitation and also in other fields. There are two major principles that are used in sonochemistry or sonoprocessing. Number one, mechanical effects for mixing and disintegration, and high energy processes for radical reactions. Most sonochemical effects occur in liquids where sound pressures are capable of disrupting the continuum, thus resulting in generation of in a process called the cavitation. So basically in the cavitation, there is a generation of cavitational bubbles, which will be discussed in the next part under the heading of ultrasonification and cavitation. Ultrasonification plays a very important role in processing of liquids by improving mixing and chemical reactions in various applications and industries. Ultrasonification led to the production of low pressure and high pressure waves, leading to which in turn led to formation of and growth and collapse of bubbles and cavities vacuum. This phenomena is called cavitation. The cavitation phenomena was first introduced by Reynolds and Parsons. These were the scientists which were particularly involved in the introduction of phenomena of cavitation. Thus, we will study from the cavitation definition itself, we get to the conclusion that in sonochemical reactor, basically when we induce the ultrasonic waves results in the creation of cavitation bubbles in liquid medium. And when the cavitation bubbles are formed, they are subsequently and soon followed by the collapse, thus resulting in generation of overheating, our high temperature up to several thousand Kelvin, high pressures up to several hundred megapascal, and shock waves. These extreme conditions can lead to various chemical changes, various chemical reactions, and thus making sonochemical reactors valuable tools in various applications such as synthesis, degradation, and material modification. So here we're going to discuss chemical and physical effects of ultrasound in the following figure number 1. This include the chemical and physical effects in homogeneous and heterogeneous system. Homogeneous system includes the liquid gas. Heterogeneous system may be liquid-liquid and liquid-solid. In liquid gas, ultrasound have vast and diverse applications in savage treatment, sonolysis, nanoparticles generation, novel materials. In liquid-liquid phase and in heterogeneous system, they have application of emulsification, extraction, savage sludge, mixing, etc. In liquid-solid phase, they have the application of cleaning, crystallization, extraction, sonocatalysis, etc. So these are the vast range physical and chemical effects of ultrasound. Oscillating devices creates vibrational motion, which in turn causes the generation of pressure waves. Pressure waves may consist of high pressure zone and low pressure zone in liquid medium. Sound waves in liquid medium are actually longitudinal in nature, and pressure waves in which oscillations of particle occur in direction of phase. The displacement around the rest position results in the formation of compression and rarefaction, which is actually the characteristic of longitudinal waves. Figure number 2 depicts the compressions and rarefactions generation in liquid medium. Cavitational bubbles are usually void, gas, or vapor-filled bubbles. Tensile strength of liquids characterizes the critical pressure for disruption. Presence of entities in liquid medium, such as dissolved gases, solid impurities, or rough walls, lowers the required sound pressure for cavitation, and thus they exist in the process of cavitation itself. Figure number 3 shows the special distribution of energy and cavitation, which actually depicts how much energy is required for the stable cavitation and how much energy and how the unsymmetrical energy is actually results in the formation of asymmetrical or the unstable cavitations. So there are particular zones when usually ultrasonic waves are applied, the pressure waves, the variation in pressure is generated. This variation in pressure resulting formation of compressions and rarefactions, which in further results in formation of cavitational bubbles. Cavitational bubbles followed by soon collapse, and this is a phenomena of cavitation. Mechanism of acoustic cavitation is there are usually three steps of acoustic cavitation. Number one is nucleation. In the first step, microbubbles trapped within interstices of particles in liquid phase aggregate together, resulting in formation of cavitation nuclei, in which, depending upon liquid purity and type, cavities are generated. Second step is bubble growth or expansion. In this stage, the microbubbles that are originally have been formed due to the induction of ultrasonic waves, they actually grow in size. So basically, when the acoustic intensity is high, cavities form rapidly due to inertial effect. However, when the acoustic intensity is low, cavities expand due to rectified diffusion, lasting another few acoustic cycles before expansion. The third step in the mechanism of acoustic cavitation is implosive collapse. In this third stage, the cavity has grown to its maximum limit and thus can no longer absorb energy. Resultantly, the surrounding liquid rushes inside cavity, causing catastrophic explosion. This explosion is accompanied by increase in temperature and pressure, which is actually observed locally. In addition to inducing acoustic cavitation in liquid medium, ultrasonic irradiation can also cause the emission of light from collapsing bubbles in phenomena called sonoluminescence, which is represented by abbreviation of SL. There are two types of sonoluminescence: multi-bubble sonoluminescence and single-bubble sonoluminescence. In MBSL, the liquid emission occurs from cloud of multiple cavitating bubbles. However, in single bubble sonoluminescence, which is represented by SBSL, liquid emission occurs from a single cavitating bubble rather than multiple bubbles. In SBLL, SL, high temperature and pressure are generated due to increase in specificity of the collapse arising from isolation of bubbles for perturbations. Next, we will go to the types of cavitation. There are actually various types of cavitation phenomena. Particularly, there are usually four types that are usually observed in liquid medium: hydrodynamic cavitation, acoustic, optical, and particle cavitation. I will give you a general view of these four cavitation. In hydrodynamic, there is a pressure variation. There is a liquid fluidity that results in the formation of cavitational bubbles. In acoustic, there is introduction and induction of ultrasonic waves that results in the phenomena of cavitation bubble. In optical, there is the introduction and involvement of light in the generation of cavitational bubbles. However, in particle cavitation, elementary particles such as neutrons are mainly involved in the generation of cavitational bubbles. Among the above mentioned four types of cavitation, acoustic and hydrodynamic are usually preferable, and they are very popular in scientific research. Ultrasonic cavitation is usually preferred over hydrodynamic cavitation due to greater energy release. There are not only many types of reactors employing acoustic cavitation, but also various sources of ultrasonic oscillations, including magnetostrictive piezoelectric transducers, which we will discuss in the next section. Next comes the cavitation threshold. On the basis of nature of motion, cavitating wires can be categorized into four types. So basically, this is the classification of cavitational bubbles that are formed in the phenomena of cavitation. So number one is stable cavitation, transient cavitation, rectified diffusion, and dissolving bubbles. Upon the application of ultrasound, small gaseous bubbles dissolve in liquid medium rapidly, and gas bubbles having certain threshold radius are stabilized. Such stable bubbles are capable of surviving various acoustic cycles. In rectified diffusion, these stable oscillating bubbles collect gases from liquid medium and increase in their size. During the refraction cycle, gases or vapors enter these stable cavitating bubbles and bigger bubbles cross the interface. In compression phase, the bubbles shrink and diffusion is reduced. So that diffusion, which was actually taking part in the expansion of bubble, is now reduced, and there is the induction of shrinking phase or compression phase. Rectified diffusion plays a very important role in degassing of liquid even at low pressure of 0.01 megapascal. Bubbles whose radius grows twice the size in half of acoustic cycle, followed by subsequent collapse and disappearance, are called transient bubbles. Most of sonochemical effects are caused by them. Rayleigh was the first scientist who first deduced the short collapse time of transient bubbles, which is actually given by this mathematical relationship, which is given in the following figure. In this mathematical relationship, there is Rmax, which stands for maximum bubble radius before collapse, which is actually the radius that is required after which the collapse takes place. Pn represents mean priming pressure, which is actually the sum of hydrostatic and applied sound pressure. Pv is equal to vapor or gas pressure inside bubble at stage of maximum expansion. Next, we will go to activation sites in acoustic cavitational process. So these are the activational sites where the chemical reaction takes place after induction of cavitation. So after cavitation, cavitational effects initiates, improves chemical reactions. So how many active sites are there in homogeneous sonolysis are sonochemical reactor? These are usually three: cavitational bubble, interface between gaseous bubbles and liquid medium, and bulk solution. In the case of highly volatile organic molecules, the decomposition either takes place inside cavitational bubble or at gas-liquid interface. However, oxidation reactions are mainly limited in liquid bulk due to interference of free radicals migrating from cavitational bubble or gas-liquid interface to bulk liquid. Hydrophilic compounds with low volatility prefer to remain in bulk solution. On the other hand, hydrophobic compounds, being highly volatile, rushes inside cavitational bubble where pyrolysis or oxidation reactions takes place. Due to high concentration of hydroxyl free radicals in gas-liquid interface, sufficient pressure gradients and temperature, the water contaminants prefer to remain in gas-liquid interface, making it most suitable reaction site. So this following diagram shows the division of the compounds and their reactions at gas-liquid interface inside cavitational bubble and in bulk solution. Next, we goes to the topic of cavitation near solid boundaries. Upon application of ultrasound, usually spherical oscillations are observed in liquid medium. However, spherical collapse is disturbed due to interference of boundaries, suspended solids, or reactor walls. So usually, in the absence of impurities or any entity, spherical oscillations take place, spherical bubbles are formed, which are followed by their collapse and cavitation process. However, due to the interference of these entities, which may be referred as impurities or which may be the solid surface of the reactor, the following changes take place, which I'm going to explain. Liquid microjet break into walls of transient bubbles, resulting in their collapse. Liquid microjets having higher velocities ranging are responsible for cavitation erosion. So basically, the cavitation near solid boundaries usually result in formation of liquid microjet, which result in cavitational erosion. The pressure generated on solid surface is strong enough to melt surface, creating pits and disturbing inorganic layer on solid surface. A liquid jet that is 1/10 of bubble diameter forms a water hammer. Water hammer having a pressure of about, which is given in the following figure, where Cs is equal to shock speed. And shock speed, basically, it is the combination of Cl plus 2Vj. Next, we're going to talk about what is the Vj in this equation. It is actually the jet speed. Ct is equal to speed of sound. Pt is equal to pressure of target. The figure number 5 shows the effect of cavitational erosion on the number of metals, as in the case magnesium, aluminium, and zinc targets, which are usually observed in the case of horn-type reactor at the reaction conditions of 20 kHz and 200 watt for 30 minutes. So these are actually erosive effects. In the case of magnesium, fatigue fracture occur with a plastic deformation. If we have note the diameter of 10 micrometer, in the case of aluminium, there is plastic deformation, and in the case of zinc, there is a brittle fracture. So these are actually the result of cavitation erosion. Next, we goes to our main topic and main section of this article, which is acoustic ultrasound and cavitation reactors. Acoustic reactor. The first question that comes in our mind when studying about reactor is that what are acoustic reactors? An acoustic reactor is a more general term that refers to the reactor or system that uses acoustic sound waves, often in the ultrasonic frequency range, to facilitate various processes. This can include sonochemical reactions, sonoluminescence, or other applications where the effects of acoustic waves on the medium are exploited. Acoustic reactors can have a broader range of applications beyond cavitation. Cavitation reactor. A cavitation reactor is actually a specific type of acoustic reactor where there is induction of cavitation in liquid medium. Cavitation reactors are often used for applications like sonochemistry, where the extreme conditions created by cavitation bubbles drive chemical reactions. In this context, the emphasis is on the cavitation process that we have discussed in detail previously. While designing cavitation reactors, there are certain factors that need to be considered. Number one, optimization of operating parameters. Operating parameters such as intensity and frequency of irradiation, etc., strongly impact magnitude of collapse pressure, temperature, and ultimately yield of reactor, which is actually cavitational yield. Thus, their optimization is very important. Here is a table that is depicting the various properties, their effects, and favorable conditions. For example, intensity of irradiation that is usually favorable is the range from 1 to 300 watt per centimeter square. It has an effect of number of cavities, collapse pressure of single cavity. Favorable condition, use pressure dissipation till an optimum value and over a wider area of irradiation. Similarly, frequency of irradiation should be in the range of 20 to 200 kilohertz. Liquid vapor pressure should be in the range of 40 to 100 millimeter of mercury at 30 degrees Celsius. Viscosity in the range of 1 to 6 cp. Surface tension in the range of 0.03 to 0.072 nano per meter. Bulk liquid temperature should be in the range of 30 to 70 degrees Celsius. And there should be the dissolved gases, which should be soluble, that aids in the process of cavitation. So these are all the operating parameters that need to be optimized in order for the cavitation reactor to work to its maximum efficiency and in order for the cavitation yield to be increased. Next, we go to the topic of cavitation yield. What is cavitation yield and why it is important? The ability of equipment to produce the desired change on the basis of electric energy used for generating cavitation is indicated by cavitation reactor yield. The Wheeler reaction was used for quantification of produced chemical changes. Following quantitative relationship was obtained that accounts for variation in cavitational yield with collapse pressure. And this mathematical expression is given as follows. Cavitational yield is equal to 1.931 into 10 raised to the power minus 14. Collapse pressure minus 6.152 multiplied 10 raised to the power minus 7. So this is the mathematical expression. This shows us the variation in cavitational yield with collapse pressure. Pressure is given in atmospheric units, while cavitational yield is usually given in terms of gram per joule. After that, we come to the topic of types of cavitation reactors. So there are various types of cavitation reactors. Cavitation reactor can be categorized on the basis of tension or can be categorized on the basis of energy deposition. So first of all, on the basis of tension, there are the acoustic cavitation and hydrodynamic cavitation reactor. And on the basis of energy deposition, which may be in the form of photons of light or which may be in the form of elementary particles like electron, there are two further types, optical cavitation reactor and particle cavitation reactor. First of all, we will discuss about hydrodynamic cavitation reactor, which are very environment-friendly and eco-friendly. Let us have a discussion and insight about it. Hydrodynamic cavitation reactor has simple design and operation. It is used to elucidate the feasibility of cavitation process at both laboratory and large-scale level. In hydrodynamic reactor, low-intensity cavitation is generated. Working principle. Hydrodynamic reactor usually consists of pump and orifice downstream of its discharge. In this reactor, cavitation cavities are generated at higher velocity and low pressure. Thus, we can say in flowing liquid medium, there is a variation in pressure, and at regions of low pressure cavities are generated, which undergo collapse at regions of high pressure. The figure number 7 shows the setup of hydrodynamic reactor. As we can see in the figure, there is the tank containing the bulk liquid. In the bulk liquid, there is a full continuous flow of liquid in and out, which acts as a coolant agent, which is very required for the maintenance of temperature. There is a pump. So we say that there is a pump and the orifice, they are the main components of hydrodynamic cavitation reactor. Here by fully or partially opening valves, cavitation number can be controlled. Furthermore, a bypass is introduced for controlling the flow rate. Factors like loss in pressure head and turbulence and friction loss affects cost of fluid pumping. High pressure homogenizer. In hydrodynamic cavitation reactor, high pressure homogenizer is used in place of ultrasonic device. It creates strong turbulence which exists in cavitation process. Figure number 8 shows the setup for high pressure homogenizer. It is actually basically it acts as a source for induction of cavitation in hydrodynamic cavitation. Just like as ultrasonic device or source does the role in the case of acoustic cavitation reactor. Merits of hydrodynamic cavitation. In hydrodynamic reactor, there is an introduction of external gas or steam bubbles that in turn assist in manipulation of pressure pulse. There is production of cavitation in shear layer, and evaporation of liquid at downstream orifice is directly proportional to area of orifice. Thus, by changing shape of orifice, area of shear layer can be changed, which in turn causes change in rate of vaporization and cavitation bubble population. If a rotating valve is used in place of a permanent orifice, the bubbles that are formed at shear layer experiences a sinusoidal variation in pressure field rather than a linear one. Variation in pressure field is also observed by installation of 2 or 3 orifices of the pump. So we can say in hydrodynamic reactors, orifices plays a very important role. However, in such case, when we introduce multiple orifices, collapse is much more violent, resulting in increase in temperature and pressure pulses. Pressure pulses in hydrodynamic reactor are low in comparison to acoustic reactor. Less rare erosion problems are observed in reactor as cavitation occurs in shear layer. In addition, cavitation throughout reactor is uniform due to the presence of high turbulence. Reactions occurring in mild conditions are preferred in case of hydrodynamic reactor. Due to large volume reactors, less energy input is required. The table shows the examples of reaction occurring in hydrodynamic reactor. Hydrodynamic reactor, there are a certain number of reactions that are usually done in hydrodynamic reactors. Number one, hydrolysis of fatty acids, such as oils, etc., that require the temperature of 250 to 300 degrees Celsius and the pressure in the range of 3 to 15 atmospheric pressure. Cyclohexane formation by hydrogenation of benzene. Tetramine preparation by hydrogenation of naphthalene. Hydrogenation of mesetyl oxide followed by its reduction to MIBK and further reduction to 4-methylpentane to ol. Sorbitol production by large-scale hydrogenation of D-glucose, which is dextroglucose. Nitrobenzene to aniline reduction by hydrogenation with catalyst. After discussing the merits, we will go to the demerits of hydrodynamic reactor. Number one, the pressure recovery at orifice of reactor is very poor. The pressure head loss is inversely proportional to orifice pipe diameter ratio. Typically, pressure loss is about 73% for an orifice to pipe diameter ratio of 0.5. Pumping costs for this reactor are very high, especially when a mixture of solid and liquid is handled. In order to produce high temperature and pressure, the discharge pressure at orifice of the pump needs to be very high. The magnitude of pressure pulses produced by oscillations of bubbles are not very high. Thus, only reactions occurring at pressure range of 10 to 15 atmosphere and temperatures till 300 degrees Celsius can be conducted efficiently in such reactors. Furthermore, viscous reacting mixtures are not preferred for such reactor, making cavitation process difficult and costly. As in the case of viscous reactors are mixture of liquids and solids, greater pumping system need to be introduced, which is actually costly. Next, we will discuss the third demerit is the heating of a cavitating medium is relatively high in this type of reactor. Therefore, cushioning of the cavities reduces the intensity of cavitation. Next, we will discuss the second type of cavitation reactor, which is acoustic cavitation reactors, and which are very important. Acoustic cavitation reactor has a very complex design and scale-up. It is helpful in the study of fundamental kinetic behavior of acoustic cavitation process. This reactor involves the conversion of electrical energy to acoustic energy, which results in cavitational field generation, which in turn produces chemical reaction. Following steps are involved in acoustic cavitation reactor. Number one, there is a power supply, after-built ultrasound generator, which generates the ultrasonic waves. Ultrasonic waves are then passed to transducers and horns that leads to the conversion of ultrasonic wave to a different amount of energy. Reaction medium, after that comes the gravitational field generation, contactive pattern, and last one is cross-chemical effect. There are various types of acoustic cavitation reactor. Two basic components are elements in all reactors are transducers and horn and reaction vessel, which can also be known as reactor. So first of all, we will discuss about transducers and horns. So what are the transducers? A device that is involved in conversion of one form of energy into another is called transducer. Ultrasonic transducers are involved in conversion of mechanical or electrical energy to high frequency are highly energetic sound waves. There are three types of transducers which are usually employed in chemical industry. Number one is gas-driven transducers. They are whistles having high frequency output. They are generally useful for breaking down aggregated particles and accelerating drying process. However, they are unable to produce high intensity. Second one is liquid-driven transducers. They're usually preferred for the generation of efficient homogenization. In whistle transducers, very fine emulsions are produced rather than ultrasonic irradiation that proves to be advantageous. Third category of transducers is electrochemical transducers. They are of the two types, magnetostrictive transducer or piezoelectric transducer. In magnetostrictive transducer, there is application of magnetic field, as the name indicates, which changes the dimension of ferromagnetic material. Usually nickel and iron is used. It has a shape of rod or bar that acts as a magnetic core inside solenoid. It produces greater driving force, however, the frequency range is restricted below 100 kHz. Nowadays, non-metallic ferrite material or ceramics are used in such transducers. The picture or the figure of transducer is given in the following page. Piezoelectric transducers. In such transducers, two or more piezo elements are sandwiched between metal masses. Piezo elements usually have composition of lead titanate zirconate. They are electrically opposite. Owing to low thermal capacity and low tensile strength, ceramic-based elements are bolted between metal masses which are either titanium or aluminum. Transducer is designed in such a way that length is half its wavelength. Such transducers are preferred as they have high efficiency of 98% and handle power transfer on the order of 500 to 1000 watt in continuous operation mode. The figure of the piezoelectric transducer is actually given as follows. And you can, if we look at the second figure, it shows a layout or a simple setup of the piezoelectric transducer consisting of a two block masses, and in between there is a piezo element. After that, the challenges that may be encountered by using multiple transducers for better working efficiency are as follows. Mounting of transducers, their coupling to liquid load, controlling interactions among transducers, ensuring reasonable transducer life, and flexibility in design for selective transducer removal. After that, we come to the part of horns. And why horns are necessary? If the transducers serve the purpose of generation of ultrasonic high energetic waves, then why are the horns a necessary component of the acoustic cavitation reactors? Actually, transducers produce very low vibrational motion, therefore application of this motion is necessary, which is achieved by horns, which does the amplification of this motion. Actually, the horn is a resonating element in compression mode. They have length of half wavelength, which can further be increased by mounting one or more horns into one another. Characteristics for acoustic horns are as follows. Number one, low acoustic loss, chemically inert, greater dynamic fatigue strength, resistant to cavitation and ruining. Horn materials satisfying above mentioned conditions are titanium alloy, aluminium bronze, and stainless steel. Among these horns, those of titanium alloy are preferred over other. Aluminium alloys are soft, thus making irradiation of liquid difficult. Aluminium bronze and stainless steel horns overheat, resulting in production of undesirable side effects. After that, we come to reactors, designs, and geometries. Ultrasonic waves generated by transducers are then introduced in reactor. There are three methods for this purpose. Number one is by immersing reactor in tank full of sonicated liquid, for example, vessel in cleaning bath, which we will discuss later. Second one is by dipping an ultrasonic source in reactor, for example, probe. Third method is by using reactor with ultrasonically vibrating walls. Power density is very important parameter in ultrasonic engineering, which is defined as the electric power supplied to transducers divided by horn radiating surface area. For piezoelectric transducer, power density is of the order of 1 to 2 watt per centimeter squared. For system with probe, the power density can be of the order of 100 watt per centimeter squared. For a transducer attached to the walls, power density will depend on mechanical strength of the walls and other attachments. Due to advantages such as greater vibrational amplitudes, energy densities, and control of energy densities within the reactor, probe system is usually preferred over two other types of systems. Now we're going to discuss about the different designs of cavitation reactors. Number one is ultrasonic cleaning bath. It is the most widely available and cheapest source of ultrasonic irradiation for chemical reactions occurring in reactor. The figure number 9 shows the setup for ultrasonic cleaning bath, which actually consists of a bath in which there is a conical flask. There are the transducers, as shown in the figure, that are attached at the bottom of the cleaning bath. There are some merits and demerits of this type of design of cavitation reactors. Merits: to provide an even distribution of energy in the immersed reaction vessel. No special reaction vessel adaptations are required. Operators can be immersed directly into cleaning bath, thus maintaining an inert atmosphere or pressure throughout a sonochemical reaction. Flat bottom glasswares are usually preferred due to efficient ultrasonic energy transfer over round bottom vessels. As we have seen in the figure, there is a conical flask used having a flat bottom instead of round bottom flask. Fourth merit of this type of reactor design is they are readily accessible. Demerits: amount of energy reaching reaction vessel is lost between 1 and 5 watt per centimeter square. Various pass frequencies or power are dependent upon transducer employed, making their comparison difficult. Medium change results in change in energy transfer from transducer to reaction vessel. Poor temperature control due to ultrasonic heating. Glassware thickness interferes with power transfer. For reproducible results, same cavitation reactor is used. For larger scale applications, usually large scale ultrasonic reactors are used. They consist of transducers attached to external walls of reaction vessel, as the figure number 10 depicts the large scale cleaning bath illustration. In this, there is a large vessel to which there are externally attached transducers. There are some advantages and disadvantages of large-scale reactors. Advantages: no contamination of reagents by erosion of ultrasonic source. The reaction vessel may be operated under pressure without the need for elaborate sealing of ultrasonic source. Disadvantages include a low-intensity, non-uniform field throughout the vessel, bulk heating of the reaction mixture not always desirable. Transducer must be glued to outside of the vessel to achieve efficient coupling of ultrasonic energy with the reaction. This is usually difficult to achieve and would probably involve significant alterations to the existing capital equipment. For 100% coverage of reaction vessel, one would need 5,700 transducers. For 10% coverage, 570 transducers are required. At 10% coverage, each transducer has to irradiate 9 liters of reaction. 570 transducers will in turn require 30 kilowatt and 30 generators to operate. These figures indicate the potential cost of large-scale cleaning bath sono reactors. Large-scale immersible transducers. In the case of cleaning baths large scale, we have discussed the transducers that are externally connected to the reaction vessel. However, there may be the transducer design in which the transducer, instead of externally connected, they are rather immersed in the reaction vessel. So we discuss them under the heading of large-scale immersible transducers. Immersible transducers are widely used in ultrasonic cleaning industry because of certain advantages: that they are relatively cheap, capable of withstanding any solvent, readily available, and can be fitted in most large vessels. Most immersible transducer reactors contain a series of transducers inside a steel box. Wiring is actually done through suitable pipes. Here the figure represents the setup of large-scale immersible transducer. There are the limitations of such transducers as susceptibility of metallic transducer over erosion, generation of non-uniform field within reaction vessel, intrusive nature as they would interfere with other equipments used, such as stirrers. Second design is the cup horn system. It is a small but powerful ultrasonic bath. It has a specially designed inverted horn that irradiates a small cup of liquid, normally water, into which the reaction vessel is immersed. Circulation of coolant through the specially designed horn assists in maintaining temperature. In cup horn system, there is good control of temperature because of circulating coolant. The ultrasound source is a modified sonic horn, and thus the power can be better controlled. The radical formation in the reaction vessel is reduced due to reduced intensity of sonication. The figure of setup of cup horn system is actually given. There are the limitations of such system, only applicable to small-scale reaction vessels, low power production in comparison to sonic horn. Next, we're gonna discuss about third type of reaction design, which is ultrasonic probe system. Amount of ultrasonic probe for the reaction can be increased by supplying power directly to reaction vessel. This can be achieved by driving probe in the reaction vessel. The metallic probe acts as a part of sonic horn that causes the amplification of piezoelectric crystal vibrations. Ultrasonic streaming resulting from the tip of the probe is enough to provide efficient bulk mixing. Most modern units have a pulse regulators. This gives adequate time for cooling to take place between sonic pulses. As after a pulse, there is a generation of high amount of energy and temperature. So in order to maintain the temperature, the pulse regulators are usually used that provides the time necessary between the subsequent or consecutive pulses. Due to intense radiation near tip, radical formation may take place that may interfere with reaction. Moreover, other limitations of using probe is tip erosion. Even if probe is made up of hard titanium alloy, tip erosion of probe either result in contamination of vessel due to eroded particles or loss in efficiency of horn due to physical shortening. Later problem can be eradicated by using screw in form of studs or seals at probe tip. Thus, this system is applicable to batch reactors. Sonic probes are effectively used in large-scale batch reactors. Next, we're going to discuss the second type of system, which is flow system. Flow systems are regarded as the best approach for large-scale sonochemistry. One method is to insert the probe transducer into a flow pipe by means of a T-section. A series of transducers could be employed to give extended treatment time. As in the figure, you can see a number of transducers, multiple transducers, they are applied in series for better application and for better efficiency. For large-scale applications and operations, the sonic horn is employed outside of the main reactor. This provides many advantages like processing of large volume, temperature, control through circulation of reaction mixture. In flow cell for forcing liquid reactants across probe, circulating pump is also required. This system can also be employed on industrial scale. The limitation of flow system is also tip erosion. Flow reactors with wall-mounted transducers. The problem of tip erosion associated with use of probe can be solved by using axially positioned transducers around flow pipe, such that tube reactor. This reactor can be used for laboratory as well as commercial scale. Tube diameter is usually an inch or two. Large diameter is recommended for bulk solution or viscous liquids. Ultrasonic energy is focused on middle of pipe. The figure number 11 shows a flow reactor with wall-mounted transducers. You can see in the first part of figure number 11 that there are the number of transducers around the surface of the tube reactor. And the next cross-sectional view shows the arrangement of transducers. High-intensity treatment involving particle size reduction requires the use of reverberatory ultrasonic mixing system. This system was developed by Levis Corporation. This system is often referred to as near-field acoustic processor. Actually consists of two sonicated metal plates that enclose a flow system. These plates act as the basis of two ultrasonic baths facing each other, a few centimeters apart. In this zone, the reverberation of ultrasound produces high intensity, contributing to applications such as reduction of size and extraction of oil from oil shale. The diagram is given as follows. Usually, these plates, in the case of the system introduced by Levis Corporation, are actually made up of stainless steel. Cylindrical and hexagonal pipes, tube reactors. So tube reactors can be of any symmetry, can be of any geometry. They can be cylindrical, they can be hexagonal. So cylindrical and hexagonal pipes particularly focuses ultrasonic energy in the middle, thus eradicating problem of tip erosion. Cylindrical pipe reactor can also be polygon type reactor. In this reactor, cylindrical tube is inserted inside outer hexagonal tube having flat faces. Circulation of coupling fluid results in cooling, thus maintaining temperature. Such reactors are used in various applications including pasteurization, crystallization, degassing, dispersion, and emulsions. Optical cavitation reactor, which are the third type of cavitation reactor that we are going to discuss. Optic cavitation is generated by highly energetic light such as laser. When a liquid medium is irradiated with a light source, the light energy is absorbed in liquid medium, which in turn leads to heating of liquid. If temperature of liquid medium becomes higher than its boiling temperature, vapor cavities or bubbles are formed, followed by growth and collapse, which is known as optic cavitation. Usually ruby, neodymium, glass laser, or any other laser employed in nuclear fusion studies is used in optical cavitation. However, the liquid under study should be inert to applied wavelength of laser. The figure number 12 shows the experimental setup for optical cavitation. In a study, Lauterbach set up an apparatus where single-stage Ruby was Q-switched with the help of nerve cell and light pulses having energy up to 1 joule and a pulse duration of about 30 to 50 nanosecond was applied. The light beam having diameter of 1 centimeter was then focused onto the liquid medium, which is usually mostly water, with the aid of single lens having short focal length 44 millimeter when submerged in water. The cavities were formed at or in closer distance to focal point. They were soon illuminated with the help of flash lamp through a ground glass plate and photographed using model 330 rotating mirror camera. This apparatus was used for the examination of cavity oscillations in the bulk of liquid medium, water, and silicon oil near plane boundaries or at air-liquid interfaces. The investigation focused on dynamic feature, namely jet formation. Holography. Holography is actually introduced for the formation of multiple cavities in liquid medium. It allows for detailed study of cavitation process. It eradicated problems associated with noise emission and erosion of probe. In holography, in place of focusing lens, plain hologram is used, which is also referred to as the holographic lens. It has simple experimental setup and has been used for generation of multiple cavities in different liquid medium, particularly water and silicon oil. So the figure shows there is a laser, there is also plain hologram, and when there are incident on the liquid medium, there is a generation of cavitational bubbles through the process of optical cavitation. Next, we are going to discuss about qualitative considerations for reactor choice, scale-up, and optimization. The first step is understanding mechanisms of interaction from the observed phenomena so that the desired cavitation field can be created on a laboratory or larger scale to promote similar interactions. The important scale-up consideration is optimization of conditions for reaction that in turn would influence cavitation. Both chemical and physical properties of reaction medium will provide an information about required level of cavitation power. Greater amount of energy would be required in case of highly viscous liquid medium. The presence of trapped or evolved gases along with solid particles will exist in cavitation. For many years, frequency was not thought to be important in cavitation chemistry. However, the use of 500 kHz irradiation has resulted in generation of hydrogen peroxide from water than 20 kHz. In addition, the size and the geometry of chemical reactor will also influence cavitation process. Efficient coupling of acoustic energy with the material providing a transmission path for the ultrasonic energy is also very important. This is usually a major step. The following features that need to be considered are number one, mechanisms of cavitation and their interaction with reactor material. Second, propagation of high frequency wave in structures. Third, acoustic coupling and excitation mode. Fourth, transducers and power generator technology. And fifth one is integration of ultrasonics into the process system. Both continuous and batch processes are preferred in commercial scale. For high energy throughput, continuous processes are usually recommended. However, a batch processes are also selected in cases where the resistance time is low, more precise control of the ingredients, back mixing is undesirable, production of different products in the same setup, production of volume is small, and a continuous process is not economical. Coupling of acoustic energy to batch or continuous process depends to a greater extent on the size and geometry of reactors. When the reactor size is smaller in comparison to wavelength of ultrasound, then acoustic source is integrated with the reactor. However, temperatures above 200 degrees Celsius, cooling, and extremely corrosive conditions may pose to be the challenge for integration of acoustic source. High levels of acoustic energy can be produced in a cylinder, channel, or a plate-like structure. The choice of the type of transducers and generators depend on the frequency, intensity levels, and intensity distribution required for particular reaction. Both piezoelectric and magnetostrictive transducers are widely used due to their numerous advantages. Acoustic power generators with a delivery capacity of up to 30 kilowatt are commonly used. If more power is required, then several generators can be used in parallel. Now we are going to discuss the factors affecting the performance of cavitation reactors and thus in turn affecting the efficiency of cavitation reactors and their cavitational yield. Number one is unequal treatment of liquid. Most devices that use the energy of acoustic cavitation are not able to provide uniform treatment of liquid in working chamber of large area. Care must be taken while designing such devices. This problem becomes particularly acute in processing of highly viscous liquid such as oil and oil residues. Under these conditions, cavitation will be more intense immediately near the source of acoustic oscillations and significantly reduced when moving away from it. which led to the uneven treatment of liquid. All this led to the need to reduce the flow rate inside the working chamber to ensure the full treatment of liquid throughout the volume of raw materials. Depending on the liquid level, more or less where acoustic energy loss takes place via air or water interface. Position of transducer. Position of transducer also plays a very important role in influencing efficiency of reactor particular. To enhance active zones, modifying the transducer positions in the case of multiple transducers can ensure overlapping wave patterns, resulting in uniform and increased cavitational activity. Various arrangements such as triangular pitch for ultrasonic baths, tubular reactors with transducers are reflector at both ends, and parallel plates reactors with irradiated plates offer options. For uniform ultrasonic activity distribution, a single transducer attached to each face of a hexagon proves effective. Next, we're going to discuss about the frequency. Frequency has a very important role in affecting efficiency of reactor. There are usually three frequency ranges: low frequency range, which is of 20 to 100 kilohertz, medium frequency range 300 to 1000 kilohertz, and high frequency range of 2 to 10 megahertz. During the low frequency range, there is a production of large number of compressions and rarefactions, which in turn delays the collapse stage and allows volatile compounds to move into gas phase. Hydrophobic compounds can easily be decomposed by low-frequency ultrasound waves. The delay in growth and collapse of bubbles result in induction of radical scavenging and recombination and inhibits transfer of hydroxyl-free radicals to the bulk solution. Medium frequency ultrasound waves releases great amount of energies into the liquid because transient cavitational bubbles collapse more rapidly and violently. Radical scavenging is hindered due to the quick explosion of cavitational bubbles. Thus, medium frequencies are effective for advanced oxidation processes employing free radicals. So usually in order to increase the cavitational activity, in turn the efficiency of cavitation reactor, usually the multiple frequencies here are also employed. Next, we're going to talk about power intensity of ultrasonic variation, ultrasonic waves. The sonochemical reactions in vectors strongly depend on intensity of sound waves. Usually by increasing power, the rate of reaction increases. Higher the sonic power generates great number of cavitational bubbles. However, these bubbles will come together leading to formation of large stable bubbles that act as a barrier to acoustic energy transfer through the liquid, which is called the cushion effect. We cannot therefore increase intensity indefinitely, and that's why here comes the optimization of operating parameters, which is optimizing the intensity of a cavitation reactor. Next, we're going to talk about acoustic energy. The acoustic of ultrasound energy at which the reactor is operating, it also plays a very important role. If an excess amount of ultrasound energy is given to reactor, then it contributes to greater heat generation leading to overheating. However, if chemical reactor operates at low energy, then the heat generation and heat loss will be minimal. Next, we're going to talk about the temperature. With increase in surface tension or viscosity, with decreasing temperature or decrease in vapor pressure, there is an increase in threshold limit. Moreover, with the increase in temperature, the effects of gravitational collapse are reduced. Different solvents, they have the different threshold temperature, and this is represented in the figure number 30, which is influence of the temperature on number of indentations in various solvents, which have been observed the solvent having the threshold temperature and having a pressure of about the 0.01 megapascal. In those solvents, there are no indentations. Addition of solids. As previously discussed, the presence of different entities, either in the form of solids, plays a very important role in assisting and in accelerating cavitation process. The solids catalysts such as alumina, silica, ceramic discs, glass beads, they are widely used in enhancing cavitational effect. Due to uniform surroundings, the cavity bubbles are spherical in pure liquid. Near solid boundary, cavity collapse is very asymmetric and generates high-speed jets of liquid. Liquid jets enter the heterogeneous surfaces with velocities of about 400 kilometers per hour and causes severe damage at the point of impact, producing nearly exposed, highly reactive surfaces. Next, we're going to discuss the influence of reactor shape on efficiency of chemical reactor. There are two primary types of reactor are batch reactor and the flow reactor. To enhance the system efficiency, it is crucial to maintain a uniform distribution of ultrasonic intensity throughout the volume, slightly above the cavitation threshold. This ensures the optimal utilization of transducer energy for ultrasonic chemical conversion destruction, preventing equipment damage, minimizing ultrasonic streaming, and avoiding localized overheating. Although low-frequency ultrasound is economical, its resonating effect poses limitations, leading to uneven pressure distribution and overheating and various other limitations. To improve the cavitation's activity and efficiency, a comprehensive understanding of acoustic pressure and ultrasound intensity distribution is essential. Utilizing a batch reactor with an ultrasound probe offers several advantages, which may include easy probe mounting, flexibility in adjusting position, there is and liquid level, convenient control of average ultrasound wave intensity, and cost effectiveness. Batch reactors come in variety of shapes that may be cylindrical or square. So here we're going to discuss about the shape of reactor effect on efficiency of chemical reactor. So to achieve consistent acoustic pressure distribution, we have the graphical representation. This graphical representation includes the absolute RMS value of acoustic pressure represented as P square conjugate P, and we plot it against the vertical distance from transducer's vibrating surface. The maximum pressure as transducer surface serve as the reference, which is actually given as P transducer. Figure number 1 depicts an axially symmetrical reactor with a pressure ratio of P over P transducer is equal to 0.303. Since this ratio is measured below the vibrating surface along the transducer axis, it indicates that the acoustic pressure is highest at the transducer surface, with local maxima occurring well below the transducer's acoustic pressure at other points. This figure is given as follows. The top figure in this page is actually including that phenomenon. The figure number 2 displays an outcome of following the incorporation of quarter wavelength coupler with adjustment made to optimize its performance. This modification aims to mitigate the acoustic impedance mismatch by converting the lower medium impedance to higher impedance, characteristic of titanium probe. The inclusion of this coupler with a resulting P over P transducer is equal to 0.4 has led to enhancement in both the acoustic pressure level and its distribution when compared to less complex configuration depicted in figure 1. The acoustic pressure distribution of 3D conical reactor reaches P over P transducer greater than 1, which is represented in figure number 3. Due to strong reflection within the sonical section and the formation of standing wave, the acoustic pressure at the cone tip is even higher than the acoustic pressure on the transducer surface. It is an encouraging result, but in the reality, this cone tip contains a very low volume of liquid and it may become easily overheated. In a flow cell, this phenomenon was also observed. Continuous flow of liquid in and out of the reactor is ensured, and it is given in figure number 4. The ratio P over P transducer greater than 1 is obtained. This result is contributed to the fact that liquid flow hinders the formation of standing waves. Experiment was also done in the case of free medium with soft rectangular boundary in a rectangular reactor, where resulting P over P transducer is equal to 0.38, showed the drop in acoustic pressure with distance increasing from transducer. Next, we're going to discuss about intensification of cavitation process. We have already discussed the factors that may influence the cavitation process and increase the efficiency of cavitation process by dragging them to the optimization level. However, there are the recent advances in the chemical industry that the certain processes combination with the cavitation process also results in increment in the cavitational yield and in the cavitational efficiency. Number 1 is the combination of cavitation and advanced oxidation processes. Intensification can be achieved using combination of cavitation and advanced oxidation processes, including use of hydrogen peroxide, ozone, and photocatalytic oxidation, only for chemical synthesis processes exhibiting free radical mechanism. For reactions in which mechanisms include pyrolysis, process intensifying parameters used, such as solid particles, purging of gases, etc., is encouraged. How much hydrogen peroxide will be used depend upon the nature of chemical reactions and the operating conditions. At low operational frequency, the rate of formation of free radicals is low. We can accelerate formation rate of free radicals by using ozonation in conjugation with ultrasonic irradiation. Decreased rates of synthetic processes are observed for reactions occurring in bulk of liquid or at gas-liquid interface. Mild acids are specifically used for the selective elimination of ionic radical scavengers that can be coupled with purging using a neutral gas to enhance reactivity. Instead of strong acid, higher concentration of mild acids is usually preferred. Combination of photocatalytic oxidation with cavitation have the following attributes. Number one, it leads to the increase in temperature and pressure, which exist in the influence on the chemical system. Second is cleaning and sweeping of titanium oxide surface allows for an access to the large number of active catalyst sites that also exist in cavitation process, increasing mass transport of reactors, reactants, and products at catalyst surface, increase in surface area due to fragmentation or pitting of catalyst. Cavitation induced radical intermediates actively participate in the destruction of organic compounds. The organic substrate reacts with photo-generated surface holes and electrons. Turbulence improves the rates of desorption of intermediate products from the active sites of catalyst, thus assisting in continuous cleaning of catalyst surface. And when there is cleaning of catalyst surface, the catalyst surface becomes available for the other reactants, and thus continuation of the process. Second is combination of microwave irradiation and sonochemistry. The recent advancement in combining microwave irradiation and sonochemistry has proved to significantly accelerate chemical reactions and various processing applications, particularly in heterogeneous systems. This acceleration is attributed to the synergistic effects resulting from improved heat transfer from microwave irradiation, and the ultrasonic irradiation have the very enhancing effect on mass transfer that occurs at phase interfaces. In heterogeneous reactions, the rate determining step involves mass transfer as phase boundaries. In those reactions, liquid jets are created as a result of cavitation that propels bubbles towards the interface at higher speeds, resulting in vigorous collisions with the surface. This results in formation of fine emulsions that are smaller and more stable than conventional emulsions, often requiring minimal or no surfactants for stability. Microwave irradiation complements these effects through enhanced heating and molecular absorption, leading to significantly accelerated reaction rates. Previous studies, such as the work of Pang and Song, have demonstrated the efficiency of combined technique, reporting increased reaction yields and accelerated reactions. This combination has also been applied to various methyl esters, showing consistently higher yields in less than a minute. Researchers like Revetto has also reported the intensified Suzuki reactions through the combined use of microwave irradiation and ultrasound. Next comes the vast and diverse applications of cavitation reactors. Cavitation reactor, mainly acoustic and hydrodynamic cavitation reactor, they are very popular in chemical industry and they are used in various applications and in various domains. Number one is the chemical synthesis. Chemical synthesis, the cavitation causes the reduction in reaction time and thus accelerating the reaction. For example, it has been shown that Diels-Alder cyclization reaction gives a 77.9% yield in 35 hours by conventional means, but application of ultrasound results in yield of 97.3% in only 3.5 hours. There is an increase in yield. The conventional way of epoxidation of long-chain unsaturated fatty acids, or esters, results in yield of 48% in 2 hours of reaction time, whereas application of ultrasound of the frequency 20 kHz increases the yield to about 92% and importantly in just 15 minutes of reaction time. Switching off reaction pathway. In some cases, the use of ultrasound switches the reaction pathway, thus changing the product distribution. For example, with conventional reaction, stirring benzyl bromide and toluene in the presence of potassium cyanide and aluminum oxide results in benzylation, which is a Friedel-Crafts reaction. However, ultrasonification under similar condition results in formation of benzyl cyanide. This is due to the fact that sonification impregnates cyanide ions on aluminum oxide, thereby masking the acidic sites and hence prevents it proceeding by Friedel-Crafts route. Second application includes water and effluent treatment, which is actually the wastewater treatment. Cavitation, mainly acoustic cavitation, is used in wastewater treatment. When ultrasonic radiations are applied, they cause destruction of contaminants. Presence of oxidizing agents such as hydrogen peroxide and hydroxide radicals, along with elevated temperature, pressure, and transient formation of supercritical water aids in elimination of contaminants from water. Adjustments in energy density, energy intensity, and the characteristics of saturating gas in solution optimizes rates of degradation of aqueous phase organic compounds. Hydrophobic compounds undergo reactions with hydroxyl and hydrogen radicals at the gas bubble liquid interface, whereas hydrophilic species undergo reaction in the bulk liquid, as we have discussed previously. Acoustic cavitation results in degradation of diverse range of chemicals such as para-nitrophenol, rhodamine, B, 1,1,1-trichloroethane, pentachlorophenate, phenol, orthodichlorobenzene, dichloromethane, sodium cyanide, and carbon tetrachloride, among others. Third application include in polymer chemistry. So basically, ultrasound plays a very important role for the degradation of polymers, including the polystyrene in the toluene, as well as for the initiation of polymerization reaction employing the free radical mechanism, like for example, polymerization of vinyl monomeric units, styrene, methyl methacrylate. Fourth application includes solo electrochemistry, ultrasound with electrolysis. Ultrasound plays a very important role in electrosynthetic reactions. Advantages are as follow: reduction in cell voltages, improvement in cell efficiencies, elimination of additives, simplification of electrolysis process. Biotechnology. Cell distribution plays a very important role in recovering intracellular proteins. This essential process in field of biotechnology requires the last amount of energy, very large energy, for satiating the high energy demand. Various cost-effective and productive techniques have been developed. Among them, the cavitation has emerged in a promising technique that requires only 5 to 10% of the total energy intake. Variation in intensity of cavitation process ensures selective release of intracellular enzymes are those within the cell wall. Low intensity cavitation, along with preserving released enzyme activity, also reduces cost. Hydrodynamic cavitation proves to be more energy efficient in comparison to acoustic cavitation on large scale. The sixth application includes in textile industry. Ultrasound improves the effectiveness of traditional dyeing methods through the dispersion and breakup of dye aggregates. This process enhances penetration of dye within the fiber by expelling entrapped air from capillaries of fiber and aspirating dye diffusion. Ultrasound also results in dye fixation, thus increasing color yield. Besides dye application, acoustic cavities have vast and diverse range of applications, including in solid liquid extraction, sonocrystallization, atomization. There is also nanoparticle generation. Additionally, in the petroleum industry, it has proved useful in refining of fossil fuels, determination of composition of coal extracts, and extraction of coal tars. Now we're going to discuss the health and safety aspects of laboratory reactors. Generally, the hydrodynamic cavitation is safe and does not have any problem relevant to noise emission. However, if the rate of flow is very high, noise emission may become a big problem. Cavitation produced during the ultrasonification of liquid sample produces a quite wide noise spectrum. This noise is released into the atmosphere, contributing to noise pollution. In laser cavitation, care must be taken in monitoring laser beams. There are two ways of controlling excessive noise: use of acoustic screen around the frame of apparatus. The second solution involves the use of box lined with sound-absorbing material. Same solutions for tackling the noise emission may also be employed in the case of hydrodynamic cavitation reactors. For acoustic cavitation, the transducer and treatment sample would be kept within the box. A 6 mm thick perspex door would be installed that will permit observation of cavitation process. A well-fitted door is necessary to reduce the noise leakage. It is possible to reduce the noise levels to 75 dB with the help of well-designed screening box. For hydrodynamic cavitation, sound-proof box can also be used for enclosing various equipments in order to reduce noise pollution. The figure number 14 shows the cavitation noise spectrum, which is actually observed in the case of hydrodynamic cavitation reactor when the flow rate is very high. The figure shows the noise level against a frequency, and it shows that particular frequency very much noise is produced and thus disrupting the cavitational yield. Now we're going to discuss about the limitations of ultrasonic reactors. In the new phase of industrial progress, ultrasonic exposure has been used across various domains, including material sciences, chemical synthetic processes, water treatment, biotechnology, electrochemical process, food industry, and mineral processing through flotation techniques. The diverse applications of ultrasound enable its integration with diverse technologies, showing its significant potential across various fields. Despite extensive research on ultrasound, only a few number of developments have been made due to following reasons. Number one, lack of experience in ultrasonic applications in areas such as ultrasound or sonochemical engineering. Second one is influence of many parameters on processes in sonochemical reactor, most of which cannot be fixed in industrial use of ultrasound. Complex multi-physical calculations in the design of sonochemical reactors. The numerical modeling of the special distribution of acoustic pressure within sonochemical reactor is a subject of particular interest among scientists worldwide, particularly in predicting cavitation events inside the reactor. I will conclude my review article with the following remarks. In all cavitation reactors, the energetic transition leading to chemical reactions have been observed. Where the primary form of energy supplied as input is electrical energy, this energy undergoes various transitions either in form of pressure, volume, and most common vibrations executed in the form of vibrational motion of transducers in acoustic reactors or liquid flow in hydrodynamic reactors. These energetic transitions finally result in induction of cavitation, which involves formation, growth, and collapse of cavitational bubbles, which in turn assist in improvement, initiation, and acceleration of various chemical or physical phenomena. By optimizing various operating parameters, pressure, temperature, volume, etc., reactor design, and geometries, cavitational yield can be increased. Design of sonochemical reactors include their geometries and shapes is a very important parameter in deciding the net cavitational effects. Use of multiple transducers and multiple frequencies with possibility of variable power dissipation is preferred for increased cavitational activity. Combination of cavitation process with advanced oxidation reduction reactions has proven to significantly expedite chemical reactions and various processing applications. Moreover, the synergistic effects of ultrasound and microwave irradiations have assisted in achieving higher yields and more efficient reactions. In this way, cavitation phenomena offers a novelty in the intensification of various physical or chemical transformations, including chemical synthesis, biotechnology, environmental engineering, polymer engineering, etc. The energy consumption is also relatively low. The numerical modeling of special distribution of acoustic pressure within sonochemical reactors is a subject of particular interest among scientists worldwide, particularly in predicting cavitational events inside the reactor. The diverse applications of ultrasound enables its integration with diverse technologies, showing its significant potential across various fields. Despite extensive research on ultrasound, only a few number of developments have been made. Now, the references for the review article are actually given as follow. And I will conclude my review article by saying that despite of a lot of improvements and lot of scientific research, there are still the room for the number of improvements and developments. Thank you.